Okay, time is up. So we will start discussing the chapter, the first section of the chapter, and Mash will start leading the first couple sections. Then I'll follow him on the rest of the sections. Okay.
So hopefully, hi everybody. Hopefully today we'll just go fluidly. I'll get us started as we opening it up with TensorFlow and have a more general discussion. And it always helps to be able to walk through the code as we do this. So we're going to use the vanilla notebook, Ariel Giron's notebook, and go through that. I have a few other notebooks, so depending on how the discussion goes, we can flip over and see a few things, and then fluidly go right into more hands-on exploration of TensorFlow with NumPy, compare and contrast that Wencheng will start to walk us through, and we'll go from there. And if that sounds good, let's get ourselves right into this. Any questions or points before we start? All right. So as we've spent a good bit of time so far, the previous chapter, which really focused on constructing a neural network, the full architecture from basic, we've covered just about every ingredient that we need. So let's look at TensorFlow and what it offers. So it's built on the Keras API, which Keras, I believe, I know Francois Cholet likes to say he did not invent it, but people still continue to attribute Keras to Francois Cholet. He has a really good book, if anyone's interested, several good books, including Deep Learning with Python, and another one that he co-wrote with the CEO of RStudio, JJ Allaire, on using Keras and deep learning using R. But Keras was released with a very, very permissive MIT license, which allowed Google to pretty much use it in every single way they wanted. And they built, with TensorFlow 2.0, TensorFlow used and leveraged the Keras API in version 1. With version 2, it incorporated it entirely. So the way I think of it, please do jump in if you have a different view, that Keras has a certain subset of core APIs, but TensorFlow expands on that and provides a lot more in order to develop computational graphs and neural networks.
Hey, Mash, I'm
Yes,
just going to interject that the
please.
Deep Learning book from Cholet, it's good, but it's compatible with the old Keras up to 2.1. So it's, you have to modify it substantially for new Keras. So people should be aware that this is not it's good to read, but it's not a plug and play anymore where you can just type in the examples. You have to modify them extensively.
Very good. Thank you, Stephen. Could you go a little bit deeper? I am curious personally, what were some of those changes and evolutions that happened with Keras along the way, going from different versions? Could you speak a few words?
So my perspective on this is that, when TensorFlow started, TensorFlow kind of is this, I hate to say it, but it's this really bastardized coding language that, people kind of just threw together, because at the time, everybody was using something called Theano and Caffe. And some people were using Torch and some people were using Lua. So you had 4 languages back in 2017 with no good interfaces. And, the TensorFlow people said, hey, let's put this, and make this run. Initially, it was like on a Theano backend, I think. And then they changed it to its own backend. So it kind of evolved out of that. And it was kind of designed for speed. So, I tried to do some stuff in base TensorFlow when it first came out, and I really didn't get much further than Minist. It was just, I couldn't understand it. And, Keras, allows you to do a lot more and allows you to actually work with it. But Keras has its own problems. And, you can do a basic classification, a basic regression, or, a basic, LSTM model with Keras. At least you could. But when you start getting into complicated, multifunction, multi-scale learning rates, multi-class optimizations, things that is a little bit more out of the bottom line, I think it's Keras failed. And that's why, people said, okay, well, let's integrate Keras and TensorFlow more consistently, and let's get things to work a little bit better. And that's why Jeremy Howard bailed on TensorFlow, because the first version of FastAI was in TensorFlow Keras, and he just literally could not implement a lot of the things that he was doing with Keras, or at least could not implement them easily. And he kind of threw up his arms, and that's why he went over to PyTorch. So that's why you have the two competing ecosystems of PyTorch, FastAI, and TensorFlow Keras. Google is going one way, PyTorch is going another way. And, for ML production, I think that TensorFlow Keras is the clear winner. But, if you're doing ML ops, ML engineering, but for actual research, most people that I'm aware of right now are doing the research stuff in PyTorch because it just is easier. I mean, I have a soft spot for TensorFlow and Keras because I've done most of my coding in it and most of my code base is in it. But, I do kind of see where people are, coming from with PyTorch. PyTorch works a little bit better, but you don't have that really good production possibility that you do necessarily with TensorFlow Keras. So that's just kind of my take on it. It's, you could get to a certain point with Keras, and as things got more complicated, things didn't work well. So everybody said, okay, we got to go back to TensorFlow. It's tricky because there's a lot of, code based on TensorFlow that doesn't necessarily make a lot of sense. It's just the way things are done. So, it's like any other language, six of one, half a dozen or another. Pick your poison. Some things are easy to do and some things are hard to do depending upon the structure.
Perhaps I can add just a tiny bit of context to that. And a lot of it has to come from industry and how the industry begins to use it, and they set the standards, and those standards really are based on actual deliverables, products that are out there. I can speak to the more prominent solutions, neural network architectures for actual products that are out there. Much of what's out in the industry that uses neural networks have to do with image recognition, video processing, sound processing, and so on. And these are products that took a lot of time and dollars invested to develop. And they've been developed over the last, 4 or 5 years iteratively. And they're largely, and as they are out in the wild even today, they were built using Keras and TensorFlow version 1. I am not aware of any code base of any product out there in the real world that is largely all image processing or multimedia processing, unstructured data processing that uses TensorFlow 2.0 yet. Everyone talks about it. Everyone knows that you have to start coding it, but software engineers are still supporting and have to, because these are products that are out there. TensorFlow version 1. I'm sure there are a number of folks here, perhaps their experience is different, working with different companies. I'd love to hear a little bit more if anyone wants to jump in.
I just have a quick question for Steve. When you mentioned, and I was looking into, PyTorch versus TensorFlow and different, comparisons, and mentioned exactly what you were saying. But I was wondering, nowadays, since we have so many cloud solutions to deploy and serve models, does that still make a difference if I just choose to use AWS to serve my PyTorch models?
I think so, and for a few different reasons. So, speaking to what Mash was saying, one of the big things that has been done with, neural network, production models is, people, the ML engineers who are building these models, I believe, are very aware of the fragility of these models and sensitivity of these models to the most basic of changes. I mean, that's why, when these guys are, putting these things out there, they're reproducing, they don't just give you a neural network in a cloud service. They might be in a cloud service, but they don't just give you that. They'll actually put a box, okay? And the box is the same box that they developed the system on because of the, the issues of reproducibility, in the neural networks. And, if you want it to run in an actual product environment, it's not a big deal to spend 10 grand for the box. You've spent $500,000 on the software already. Just reproduce a box at the installations that you're going to be using it with. This is coming from contacts of mine in the oil and gas industry who've had this issue and have done that. Okay. In terms of, what you use, I believe that Google's strategy and what TensorFlow 2.0 is about is TensorFlow 2.0 is about turning, or at least was about turning making ML ops easier, okay, so that it is more of like a dashboard kind of connect the model situation where you put data into GCP and GCP does all these wonderful things for you, modules that you've plugged in. The amount of hyperparameter tuning is minimal. You're doing auto diff, you're doing, auto ML, you're doing auto augmentation, that sort of stuff, based upon your flow that you make in GCP, and then spouts your, result. That I think was Google's strategy at least a year and a half ago. I don't know what it is now. I haven't had any, I haven't talked to my contacts lately, so I don't really know. PyTorch is more implementable, and you can get into, its guts a lot easier necessarily than TensorFlow. But the productizing of it, I don't believe is as good as TensorFlow. It might have just kind of gotten sort of there, but I'm not aware of anybody who's doing stuff in PyTorch. It could be happening in the ML, health world. I think it very well could be happening, but I don't know that it is.
I have to agree entirely with Stephen. In production ML ops types environment, I have yet to see PyTorch out there as well. However, researchers swear by PyTorch when they're doing neural networks. They seem to just prefer PyTorch. And if you're either coding everything in R because you just love R, or if you're that ambitious researcher that prefers to use virtual machines and blah, 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 and so on, you're using neural networks with Python, you're probably using FastAI and PyTorch.
I think people are using, I'm using both.
You're using both TensorFlow and PyTorch?
That's because I'm crazy.
You absolutely are. All right, so let's continue on. And as you, there's a really wonderful diagram. This is specific to TensorFlow 2.0, where it builds on and lists out all the different APIs. And as you can see, as we've been discussing, you have everything you need, all the tools needed like auto diff, pre-processing, visualization with TensorBoard built in to TensorFlow, built in on top of all of the Keras APIs, optimization, controlling for loss functions, everything you need fundamentally, as far as I can tell, for data structures and data pre-processing, and of course your basic linear algebra libraries and so on. So everything is there. And then I'm sure we'll be going a little bit deeper into the lower level APIs that TensorFlow 2.0 allows. So that's the general gist of it, where when you begin to call it, Google has done a pretty good job of being able to give you the foundations for being able to architect your neural networks in the way that you need to. It's flexible and so on, but at the same time, keeping a very close eye and flexibility to operationalize and productize your models. So this allows you to save he didn't go into the code here, but I did download a separate notebook from Google, which showed how you can use the Keras API to be able to save your computational graphs, your model, your select model, and allows you to do the transfer learning that we'd studied earlier pretty easily. We don't have to go all over the code just yet, but let's move on. Now, TensorFlow itself works in very similar ways to NumPy, with some important distinctions. One, of course, right top of mind is when you work with NumPy, and it's basic to Python, you are creating effectively an alias. When you transform a NumPy matrix, you're still calling the same original matrix, just alias to the transform function. Whereas in TensorFlow, it will actually truly make a deep copy of a particular matrix when it does a transformation. Something to keep in mind, of course, you're working on a Google environment or anything Google develops, they don't really think disk space is usually a concern. It's a service, just pay for it. Any questions up to that? All right, moving on, there's some general right in the code where you can look up a TensorFlow. If you do a type on a tensor is a float 32. I think they've increased that. I do remember seeing it somewhere. But these are, you can see what a scalar and a typical matrix would look like. And when you can also index a tensor, just as you would index NumPy matrices. You can run all sorts of various operations, just as you would, but keep in mind how it begins to work, where you are creating a different data frame object in TensorFlow as opposed to in NumPy with its aliases. And for my part, that's largely it for the introduction. It begins to open up. He mentions a little bit about Keras's low-level APIs, which I'm sure we'll have a chance to study a little bit deeper. But again, the original point that I had made earlier, Keras offers some very basic core capabilities and functions. TensorFlow 2.0 certainly builds a lot more over it. If we continue that line of developmental strategy, I suppose at some point it'll really just only be TensorFlow new versions that we will be talking about. Keras will just become subsumed as just another layer that happens to be in there, unless there's more capability and flexibility at the lower level APIs from Keras that may be useful for you as you architect and develop it. I'm certainly not at a level of skill to be able to do much of that yet.
Hey, so I do have a question. The notebook right at the top, the cell right at the top, 173. So the one that you got.
Yeah.
And this is a question out to anyone. TF.newAxes That was quite interesting because I haven't seen the triple dot notation, but tf.newAxis is actually a none type. So if you do a type, so if you just, I don't know if your notebook's working, but if you just do a type and then you just copy tf.newAxis, that's an untype. And I couldn't get my head around why you might have this. Does anyone have a view to that? So if you do, if you open a new cell and you do a type and then you just do none as in capital N-O-N-E. So the Python none type, it's exactly the same thing. And if you look at if you do a help function, you see they're both identical. So it sounds like tf.newAxis actually just points to the none type. But I don't know why you'd have a data type that is a none type. So if anyone has a view, that would be helpful.
Yeah, I noticed that too. If anyone knows a little bit further.
I mean, my only guess is that, you know, because it's TensorFlow tends to make new classes of everything, while the classes are downwards compatible to NumPy. Their class sits on top, so that may be, part of why.
Yeah, but I haven't come across a NumPy type that is of type none. So this is the data type, right? Which is typically float 32, float 64, and so on. Why would you have a data type that is of type none? What are you achieving there?
NumPy.newAxis is non-type too. So
NumPy what? Sorry.
NumPy.newAxis. It's similar to NumPy.newAxis. It's also none. And if you just do none, it's the same thing. You don't have to do tf.new. I think NumPy, at least for NumPy, you don't have to do NumPy.newAxis. I think if you do none, it's the same thing actually. You can use
sure.
In place.
So I guess if you think about it, you're operating on a type, right? You're not trying to make it to a new type. You're operating on a type, so it has to flow through to the same type that you started out with the new axis, and that's why the type itself doesn't change. It inherits the type, perhaps. You know what I'm saying?
I don't, because so you're creating a tensor with a certain number of components or values, right?
Right.
So why would you have those types as none versus what we're used to seeing, float 32 or any other type? That's my question.
Mash, if you change like cell 180, cell 180 tf.newAxis to none. Just change that to none.
Yeah, and I think you'd get exactly the same thing because it looks like
Exactly.
tf.newAxis does exactly what none type does. So it probably is an alias for that. My question is why would you have that? It's not is np.newAxis same as none. It's why would you have that?
I'm not smart enough to know.
My guess, John, is that none just provides you the ability to add the new axis, and then if you don't know the type, you can always fill in the type later of whatever the data in that axis happens to be. So none provides you the flexibility to just create an axis without giving it a data type.
I agree.
Oh, okay.
You have just added a dimension to your tensor without specifying what the data type is for that dimension.
Right.
Hey, Wenchang, are you gonna go over the cast and the type conversions at all, or is that something that you're not going to speak to? Because I just have a point or two I'd like to share on that if you're not going to speak to that.
I'm gonna go through what's in the notebook, and I don't think he touched too much on cast and type conversion. So yeah, you can certainly speak to that. Yeah.
Do
Okay.
you want to take it now?
If you don't mind, one of the things that I think is kind of maybe under mentioned that's important, particularly with TensorFlow and Keras, is the ability to, switch around your types a little bit because the tensors in TensorFlow are immutable. This actually becomes a practical issue quite a bit, especially when you're working with images, and we are reshaping and casting frequently. So I think this is important to know. Like for example, when you're trying to add a float 32 and a float 64 together, or an integer, you can't do that, and you have to use tfcast. That's very helpful. Also, I want to mention. Yeah, that was my main point. Just be aware that the precisions change, and also there's mixed precision that is used in a lot of the new NVIDIA algorithms. I know that StyleGAN 2 uses mixed precision because it won't run on my box. So, you're switching, perhaps between 16, 32, and 64, precisions on, the basis of TensorFlow and also then CUDA as well. So you just have to kind of be aware of that, and if things start breaking, be aware that you can cast them to different formats. That's all I wanted to mention.
All right. Wenchang, do you want to pick it up from here?
Oh, yeah, sure. I mean, if you finished.
Yep.
Okay, sounds good. Okay, so let me start, and thank you, Stephen, for bringing that as well. And I was planning to touch upon a little bit on the 32 and 64 bits, as Jeroen kind of mentioned that as well. I think NumPy default is 64, and but TensorFlow's default is 32, and he was saying basically it actually doesn't matter as much, especially when you try to do deep learning, and TF.32 or flow NumPy.flow 32 or TF.float 32, you save half of the memory, and it runs a lot faster. So, and also TensorFlow, I think what's good about TensorFlow is he also mentioned it doesn't do automatic type conversion, and I believe pandas might do that, because sometimes I run into type problems with pandas, but TensorFlow apparently doesn't do that. So anyway, so let's go through some of the concepts, some of the other concepts regarding TensorFlow. So as Mesh kind of pointed, a lot of stuff came from NumPy, and they're quite similar. And so let me jump into that. And we were talking about conflicting types, right? So notice this, right? This actually doesn't add, and it will give you an error. And it says cannot compute ADDV2 as input 1 was expected to be a float tensor, but is an integer 32 tensor. So this is integer 32. This is float. And so you can't really add these two together. And if we just do type, Doesn't show me that. Okay. And basically, you cannot do add these two together because it's conflicting data types. TensorFlow has very strict rules on what you can add together, what you can multiply together. Usually has to be the same type. And as now, if you just put a dot here and specify the D type equals to tf.float64, it wouldn't add either. So because this is 64, this is 32, and so it wouldn't add either. Let me just do type. Yes, so this is 32, and if you specify that, then it becomes tf.float64. So that wouldn't add either, and the error says exactly that. Would expect it to be float tensor, but it's a double tensor. But so tf.float64 is called a double tensor. Now tf.float32 is called float tensor. So there's a name difference here. Okay, and if we just do tf40, that's tf.integer32. So usually TensorFlow would go with 32 regardless as a default for integer or float. Okay, keep that in mind. Okay, and let me see if I want functions. Yes, I changed the order a little bit because I feel like it makes more sense to actually talk about tf.variable here before you dive into arrays, tensor arrays, and rack tensors. So, and this kind of goes back to I think Python actually does not have constant, but JavaScript does. And I think TensorFlow kind of adopts that concept, like, there's tf.constant and you cannot change that. But there's also tf.variable, which you can, modify. So, and he kind of gave a quick example, v equals to tf.variable, thus, and you can change that by just dot assign 2 times v, okay? Then it becomes like 446. So it basically broadcasts over each element, right? So it becomes 446, 8, 10, 12. And if you want to assign, index 0, 1, which is 0, 1, which is this number, to 42, then it becomes 42. But if you do this, if you don't do dot assign, if you just want to do this, it wouldn't work. So you have to call the dot assign, kind of change that. Okay, and again, Python actually doesn't have this, native Python doesn't have, constant variable, a constant, I should say, that you can define, but TensorFlow allows you to do that. Okay, JavaScript does have that, and it goes with const. Then you define the variable name, and if it's something that you want to change, then it'll be let variable name. So yeah, okay. Strings, I thought that's pretty straightforward. You basically just put in a string. And he talked a little bit about Unicode, and I'm not too familiar with the concept of Unicode. Does anyone want to talk a little bit on that?
Yeah, it just allows you to be able to represent strings that might not be your typical English characters. So things like, if you want to include French accents or other languages, it extends on what you had at UTF-8, I think it was.
Yeah, Okay. So does that it just converts them into numbers, right?
Yeah. So you'll have a code for each.
Got it. Okay.
Yeah, it's also very useful for, as I said, it's very useful for characters in other languages. You can actually directly use the keyboard to type in characters in other languages, and it will also communicate back to you using the characters of the other language.
Got it. Got it. Cool. So we might, we might need to use this in NLP, if you're dealing with other characters. Cool. So
it's usually UTF-8 doesn't really get into so many other characters. UTF-16 is the one which has a very good range.
UTF-16. Okay. What are the differences between UTF-8 and UTF-16?
So UTF-16 can accommodate a much wider variety of characters, whereas UTF-8 is more or less very close to what already exists with ASCII.
Got it. Got it. Okay. Cool. Cool. Thank you. Okay. String arrays, there's a tf.strings, and you can kind of pass your constant variable in, then, then it'll convert and specify the units equals to UTF-8 characters, and we'll kind of convert that into UTF-8 characters.
Stupid question, but
yeah.
With NumPy and TensorFlow.
Yeah.
Oh, I'm okay. No. It's a stupid question. I thought B was like a code, but it's really just the variable. Never mind. Thank you.
Yeah, it's I had the same question. I was like, what is this B? And it's just it's the same thing. Even if you don't type in a B, it will still be there.
No, B means it's a byte type as opposed to a string or a character type. Yeah.
Yep.
Sorry, that means what?
It's a byte type. So so for example, if you send data across, it's sent across as bytes. So you can't view it. So it's basically like if you try and open an Excel, if you try and open a PDF document, it's all in byte types as opposed to just standard text.
Okay, so it's not ASCII. It's another encoding format.
Yeah. Yeah. It's like when you transfer files, it's transferred as a byte encoding. So that's what it's normally used for.
Gotcha. Thank you.
I've seen R before as well. Does anyone?
That's normally so that when you're working with paths, you can use it with Unix or Windows paths, and you don't get messed up with that, because that means especially when you have the right slash and so on, that can sometimes be confusing because there can be other meanings for that, especially right or left slash with Windows, and R just means you won't have that problem with. So it's used for that, and it's also used in regular expressions.
Yes, absolutely. Great. Thank you so much for explaining that, John. Very helpful. Cool. Okay. So then tensor arrays. This is very interesting. And what it does, it's a class wrapping up dynamic sized. And when I say dynamic sized, you'll see what it is. And it's per time step. And it's write once tensor arrays. That's exact definition coming from TensorFlow's website. And if we specify array here, tf.tensorArray d type equals to tf.float32 size equal to 3, and you can write these tf.constant in, as a time steps. I believe these are time steps, and if you call them, it's array.stack. Okay, and then you can see that 1, 2, 3, 10, 5, 7. But if you read 1, which is reading this, it will make this 0. So if you read once, if you look at this becomes 0. And if you read this in step or index 0, then this becomes 0 as well. So this was very interesting. I haven't used it before. And would love to know more about this. Very interesting data structure. Cool. So anyone else wants to talk more about that, who has more experience on this tensor array?
Never touched it.
Cool.
Hey, can I just ask a question of someone? I'm just looking at the ragged tensors.
Mm-hmm.
Oh, that's next?
Yep.
Never mind. Shut up.
Cool. All right. So yes, that's exactly what I want to talk about next. I don't know why his definition on page 383 says, and I'm going to read exactly. It says it represents static list of lists of tensors where every tensor has the same shape and data type. The tf.ract package contains operations with ract tensors. Now, I don't think they are actually same shapes. Then that's exactly what the definition is. It's not supposed to, well, you're supposed to be able to store different shapes of tensors and versus tf.constant. So I don't understand why he said where every tensor has the same shape and data type. So I was a little confused. Anyone else has any answers on this? Page 383.
Oh, I just looked at the TensorFlow documentation on that, and I think you're right. There's a typo there. Maybe it'd be helpful if you just I linked it into the chat. If you just if you just display that page for everybody, and then we can just kind of look at it.
Yeah. So let's. It's exactly here, right? So it represents a list of lists of tensors where every tensor has the same shape and data type. And when I looked it up on your data this is rack tensors, okay? And it says your data comes in many shapes. Your tensors should too. Rack tensors are the TensorFlow equivalent of nested variable length lists. They make it easy to store and process data with non-uniform shapes, including variable length features, such as the set of actors in a movie, batches of variable length sequential inputs, such as sentences or video clips, hierarchical inputs, okay, text documents that are subdivided into sections, paragraphs, sentences, individual fields in structure inputs, such as protocol buffers. And it's very obvious, right? You don't even have to have any numbers in one of the lists or tensors. And you could have various lengths as well. So I think that was a mistake on the book.
I mean, I actually haven't used this before, but I think this is, to me, looks like it's for NLP. It's almost like trying to parse out, you know, the characters and words in a sentence. So you get, you know, maybe, you know, if you're doing an attention model, you're getting like, you know, 7 words that you're taking, and the words are a variable length, you know. So that to me seems what this is used for. But I'm not an NLP guy, so I've not, you know.
Yeah, I think you're exactly right. We had we ran into tf.rack tensor before. I think it was probably either birds or there you go. So sentence 1 and sentence 2, and this is birds fine tuning. And So sentence 1 is, I believe, Portuguese. Well, no, actually, this is identifying whether the same whether two sentences have the same meaning, and so use tf.rect constant and encode sentences in sentence 1, encode the sentences in sentence 2. So sentence 1 and sentence 2. So start by encoding all the sentences while appending and packing them into rect tensors. That's where it was used.
I think the key thing to ragged tensors is that it's a list of lists. And if you think of it that way, then what Jeroen says on page 383, while misleading, is actually the right thing. What he meant to say, I think, is that each list has the tensors in each of the list. Okay, so you have a list of lists of tensors, right? And each element in that list of lists is a list, and each element of that list has tensors of the same shape in it. So you could have a collection of lists of tensors of different shape, right? If that makes any sense. The list of lists would be a collection of lists, and each list would have to do with tensors of a certain shape. So you could have text data, image data, tabular data. You could have them all combined into one object. And I think that's what a ragged tensor is.
Why would it have the same shape?
Well, each tensor in one of, okay, so think of a list of lists, right? Now think of one of the items in that list of lists. That item is itself a list, right? And then, so what I'm saying is that every element in that list, every element in that item, every element in that list has tensors of the same shape. But the overall object is a list of lists. And so, and each list has tensors of one shape, of a different kind, a different shape. So what I'm saying, for example, is one of the elements in the list could be a list of tensors of text documents or of text objects. And another element could be a list of tensors of image type. And another element could be a list of tensors of array type.
So you're saying so and long here are the same shape? Is that what you're referring to?
No, I'm looking back at his definition on page 383 of the book, where he defines
what in this example, what's the same shape when you were explaining?
Oh, okay. Let me see that. TF.ragged tensor, blah blah blah. Oh, I see. In this case, well, in this case, each item is a list of numbers, but in a general case, each item could be a list of tensors. It could be a list of tensors, not just numbers.
Okay. Well, anyway, that's the definition, and we can, argue whether, what Jeroen meant. But this is the TensorFlow's definition on the website, and we'll just go with it. So, okay. Anyone else has any comments or questions on this rect tensor? Okay. All right. So, and as you can see, I'm not allowed to input 1, 2, 3, 2, 3, 4, 5, 6, 6. Okay, because it literally says can convert non-rectangular Python sequence to tensor. So this has to be rectangular, and but rect constant can store a data structure that's not rectangular.
Is it rectangular, or that it has to be a perfect a matrix?
Well, a matrix is rectangular, right?
Because the shape for that constant isn't a single value. It's you've got those two brackets inside the parentheses. So it's how do you call it? You and I think, discussed this during our hackathon some really late night. Like a dictionary of lists or something. And so you're trying to force that into a tensor.
I forgot. Yeah, but all you have to do is literally do well. I shouldn't change this. So it has to be this, or this, right? It just can't be this. So they have to be the same, rectangular, basically. Yeah, of different shapes. Okay, cool. Anyone else? Okay, sparse tensors. Basically, it allows you to store a sparse matrix in an efficient way, and you just have to specify your indices for the values. So if it's so it's basically 0, 1 will at index 0, 1 will store value 1. At index 1, 0 will store value 2. Index 2, 3 will store this. And the entire if it's actualized format, if it's sparse format, it's 3 by 4, and but it wouldn't show this if you just print this. It would just say, because it's stored in the sparse tensor object. However, if you call this toDense, then it will show the sparse matrix and what it actually looks like. Okay, and you can broadcast, times 2.0, and every value will be multiplied with 2.0. But however, you cannot do plus. You cannot broadcast plus operation. I don't know why that this is set up this way. And obviously the book actually didn't touch on all these different structures in coding. Anyone knows why this is set up this way? Why plus operation is not allowed?
It seems the plus is not happening only because of a difference in types.
What do you mean?
So they say they have this type called sparse tensor, and you have another type called float.
Yeah, but I could do it here.
That was multiplication.
Right. No, that's my question. Why is multiplication allowed but plus not allowed?
Because in multiplication you don't really have to change anything. In plus, it's a little bit ambiguous. In multiplication, it's not ambiguous.
Okay. Okay. And yes, so multiplication is allowed, with matrix multiplication as well. So you can do this sparse dense matmul S4. Okay. And yeah. And notice, when you have 0, 2 and 0, 1 here, it doesn't allow you to actually toDense because the index is out of order. So you should have 0, 1 at first, 0, 2 on second. Then it will allow you to do that. But you could also do reorder. Then it will allow you to call the toDense method. Okay. And in the end, there's a set data structure that TensorFlow defines. I think this is relatively similar to Python's set operation. You can call difference, intersection. Those are all available in Python, native Python as well. Okay, so that's that. Anyone else has any questions before we kind of dive into PyTorch?
Yeah, I have a question. What you have shown, what we have seen in this notebook are some basic operations. I was wondering, is it really possible to, let's say we take the standard random forest regressor, which is available very easily. Is it possible to run a random forest model using using this one, or it's
TensorFlow data types?
Yeah, so let's say I'm doing a regression with real numbers using random forest. Instead of running it on the CPU of my computer, can I run it on using TensorFlow?
Yeah, why not? You don't have to use a GPU to run TensorFlow.
No, it's not that. What I meant is that what this exercise has shown us is how you can run simple additions and simple manipulations, not running somebody else's algorithm. So the random forest is scikit's algorithm, and it's a sort of a black box for a user, right? You are not defining the actual operations. It's already defined in the library. So can I actually run that through TensorFlow? Because then things should happen much faster, isn't it?
Yeah, I don't see why not. I don't know whether you can run tensors, tf.tensors in scikit-learn. I don't see why not, but I haven't tried it before. Anyone else has any?
No, I would have thought that scikit-learn is implemented on top of NumPy, and so so you'd think that it would work with NumPy. I wouldn't expect it to work with tensors, and I don't know why you think it would be faster either.
Let me do a quick search.
Yeah, but
I think
have a go. So if you've got something with random forest, change it from NumPy to tensors, and then have a go. I doubt it will work because it sounds.
I don't think it's going to work. I don't think scikit-learn processes tensors, but the broader answer to your question is that you could write your own, let's say, logistic regression algorithm or whatever linear regression algorithm in using TensorFlow's,
I
data
agree with
types
that.
and so on. Yeah,
it's easy to write your own ordinary regression algorithm, logistic regression, etc. But I don't think it's that easy to write random forest regression. I mean, random forest algorithm.
Well, random forest algorithm is not a trivial algorithm anyway, so it would be difficult to code that. It would be difficult to code that in NumPy, but I think that one could code it up. There's no reason why one couldn't code it up in TensorFlow. I'm not sure why you'd want to.
Just to speed it up, because at this moment, when I run that regression on random forest, it takes about an hour to solve it.
Oh, I see. You're thinking maybe you could use GPU to you could maybe make use of the GPU to solve to do random forest, or
yeah, something like that. Except you can directly say that I want this cell in Jupyter to be solved by GPU. That's a different approach. I thought because TensorFlow has streamlined how to do operations quickly.
So if random forest under the hood had a whole lot of matrix multiplication operations, then a TPU or a GPU would make sense.
Okay.
I don't know. I don't know enough about how random forest works under the hood, but that's where you would get the edge, or that's where you get the speed performance, not otherwise.
Of course.
Yeah.
Can I just make a comment?
Go ahead.
I'm sorry that I was
no worries.
Off of my headphones. Someone else said that, and I'm repeating myself. I apologize. But are y'all aware of the Rapids Docker that NVIDIA has? So NVIDIA has been putting out GPU accelerated ML algorithms, but not just deep learning. They're not just using CUDA for deep learning. They're trying to now use CUDA for more traditional ML, and particularly for the random forest use case, and then also XG boosting and things like that. So it's an early or implementation. I don't know if it will have all the things you want, but I do believe that random forest has been included in NVIDIA Rapids, so you might want to check that out.
Yeah, because algorithmically, random forest is what they would call embarrassingly parallel. You run all these trees, you run 1,000 trees, and they're all independent of each other, so you can run them through parallel processing, running them through the GPU. So that's probably a good application of GPUs.
Yeah, so what I'm showing is exactly the Rapids CUML. It does have random forest classifier, and it has this Medium post has a comparison between CUML and sklearn.
Okay, this is good. So this is called CUML Random Forest Rapids.
Yeah, this CUML
Yeah, I put
comes
the
from
link in
Rapids.
the chat for y'all.
Yeah, CUML comes from Rapids, and also there's Pandas. There's basically GPU for Pandas also in Rapids. I believe it's not just CUML, it's CU something else as well. I forgot what it is.
So what kind of packages do you need to implement this? Only Dask is good enough?
What do you mean?
I mean, you have to have a GPU. You have to have a GPU,
right?
Okay, that's compatible. So you have to have a compute level of at least 3 or 5, I think, on it. So that's basically going to be anything upwards of a 1080, and you have to also, download the Rapids package or Docker, and use that. I think it's a package. You can go to the link that I gave you, and you can search up on how to install it. I've used it as a Docker, but that's because I've gotten really frustrated with reproducibility over time. So I'm only using Dockers for my deep learning stuff and GPU based stuff. And I don't think it really runs necessarily only through Dask. I think this is the package itself.
I see.
Rapid.
Okay.
Yeah, and I was just saying QDF. So this is like the Pandas before, like Pandas for GPU.
Yeah. So it would be great if you could just post a couple of links on the chat, and then
if someone can do that would be great. And so that's Rapids, and well, I'll post this to the chat.
So your use case is you're having to use random forest, and it just takes too long. It takes an hour for you to be able to calculate the stuff you want, and so you're looking for alternatives.
Yes, that's as simple as that.
And also TensorFlow has boosted tree. I just looked it up. So this might be interesting as well. So gradient boosted trees.
Just one question: wasn't there someone who was supposed to do a demo on Rapids, or has that already been done?
It was already done. It was Salim.
Right.
And it's probably recorded somewhere.
You might want to check that one out.
Yeah.
Okay. Thanks.
Great. So, we got 10 minutes left. Okay, so I literally pulled a PyTorch basics from somewhere else. There's a book called PyTorch NLP. I'll post this. I mean, I wouldn't recommend to buy this book, but the basic PyTorch notebook came in handy, so I just basically grabbed it. Okay, so And
Jeremy just put out a new book on PyTorch with Fast AI. I have not actually read it, but I did get it. I like to get books. I don't necessarily use them.
Me too. Me too. I have to say I'm the same. Yeah. Cool. So let's go through some PyTorch. I was just testing some code. Okay. So again, I believe it's pip install torch if you haven't, run it in. So I don't have to post this in chat, but like if you don't have PyTorch, you should kind of, install it just to, quickly. You don't have to have this notebook. I mean, it's literally just, this, right? So you can just type it in and try. Okay, great. So this is just a function to describe, dot type, dot shape, and format with this. And again, it's basically it's torch.tensor, and there's torch.tensor and there's torch.tensor. So one is a little different from the other. And I think I was looking up the definition on one second. Let me just difference. Okay, yeah, got it. Sorry. Torch.tensor infers the D type automatically, while torch.capitalized tensor returns a torch.float tensor. And this person recommends to stick to tensor, torch.tensor lowercase, which also has arguments like D type if you would like to change the data type. So just a quick thing, to keep in mind. Torch.rand, very, handy methods, basically gives you, and you specify the shape, gives you these, I believe it's similar to random.rand. Okay, and this, yeah, it's similar, I think. And there's rand, RAND versus RANDN. Okay, and torch.zeros, again, specifying the shape will give you a bunch of zeros. Torch.ones, if you do .fill, it will give you, it just fill all the numbers for you with the number you specify. And you can kind of pipeline that, just, specifying the torch.tensor, then fill that.
So I've got a question, because one of the advantages of Torch is that the tensor allows you to capture the gradient also. Is there such a facility with TensorFlow version 2? Because I know it's not available. I don't think it was available in 1.
I don't know that question. The answer to that question. Anyone else has any answers? And when you mentioned like PyTorch tensors capsulates gradients, can you be a little bit more detailed?
Yeah, sure. So you can specify, you can ask it to basically start capturing the gradient, and that's why you can do things like autograd, where it automatically calculates the gradient for you. And that's what made it very easy to use. Presumably there's something very similar with TensorFlow. I haven't used TensorFlow.
TensorFlow has auto difference. And there's gradient tape. There's gradient tape for automatic differentiation, that is computing the gradient of computation with respect to some inputs. So automatic differentiation is useful. Yeah, so you might want to look into this. but I'm not too sure if this is comparable to PyTorch's implementation of AutoGrad. Okay. Anyone else?
The question about the production comment, because in AWS and anywhere, Azure and on-premise, a lot of machine learning models have been in production. So I just wonder, is that got to be, other than TensorFlow, there are a lot of other tools, frameworks used for production, right? So the comment about TensorFlow mostly in production, how is that? I guess how to understand that, I guess.
I was literally looking up while Stephen was talking about that, and this is PyTorch's official website, and they explain, serving PyTorch models, and it was saying basically, if you can use the cloud for your application, there's several great choices. AWS SageMaker, you can literally do that. All the resources from AWS for working with PyTorch. There's SageMaker Python SDK, and this was the link. Use PyTorch for Amazon SageMaker. So there's this, and deploy PyTorch models. So and the thing is, that's what I guess that was one of my questions as well. And Steve kind of touched upon it, because I was thinking, if I just build a model and I build an API gateway and I let SageMaker handle the model and use API gateway to access the SageMaker model, then isn't that pretty scalable? To a way to serve your model. So I don't know.
Yeah, then it doesn't really matter, right? You could use TensorFlow, you could use PyTorch, you could use whatever you like.
Right.
Exactly.
I mean, it's certainly scalable, but you're going to have to incorporate that scale into what you're doing. If you're just running inference, and you're trying to run quick inference, it's not you can just spin up another container. But you might even be able to run inference depending upon the need on a CPU, model. You have the time consuming part is the training. Now, if you're serving up stuff to like mobile applications, that's a little bit different. You want as fast as possible, with the because you have the lag of the data lag, and from the wireless itself.
Mm-hmm.
I can provide a little more context with the real world example. So this is one of the things that I and my team are working with starting this past week, where we have to develop an entirely new API layer, because we are productionalizing our core Python engines, and they will run on our virtual machines. And so as the needs come, we can scale them up and higher and higher. And it's largely NLP processing, NLP workflows, where we're reading through a massive number of documents, structured, it could be spreadsheets, financial statements, legal contracts, where we have to identify certain types of language in these legal contracts and so on. So processing these documents are complex as it is, but we're trying to develop these API endpoints. And so I had one long conversation meeting with one of our data science engineers, where he just wanted me to list out all of the potential use cases for these API endpoints. If you guys know exactly how you could take this, the idea is, whatever notebooks you have, you containerize them. And so your API endpoints really are connected to those containerized instances of that code. You have one that will do something, takes a document, recognizes a specific type of governance language or a termination clause or so on. And so that's the kind you're going to call an API to say, I'm going to pass you a location of 1,000 different contracts, and for each one of them, compute that type of language and give me a probability associated with it, and do it as quickly as possible. That would be the definition of one API endpoint. Would that work with something like this?
If I understand correctly, I'm just beginner in all these areas, but my understanding is in the TensorFlow side, the focus, especially Google, they focus on Kubeflow, right? So that basically run your machine learning model on Kubernetes clusters, right? That's the and they build really a really end-to-end flow to enable that. That's why you're seeing more and more. This is running on Kubernetes containers, basically,
right?
Which is not necessary, which is not for sure necessary because AWS doesn't do that before. So, and for another one, like MLflow is similar, but it doesn't cover that much. But it just focuses on manage the model, etc. Right? So if you use MLflow versus Kubeflow, then you don't necessarily use Kubernetes. You can still orchestrate with the other services you have, including Databricks and etc.
Yes.
Run your workflow without even Kubernetes.
A very good point. But I think, as I understand it, the different distinction between Kubeflow and MLflow is MLflow helps you manage your models. So you have a Kubernetes, you have a pickle file, your model, your XGBoost model saved as a pickle file, or your H2O AutoML model saved as a Mojo model optimized Java object, or you have a TensorFlow model saved locally as it's a computational graph saved as however way TensorFlow saves its models. I think I had some code saved elsewhere. That's if you're calling only that model, then you can use MLflow. However, if you take your entire Python code and you've turned it into a Kubernetes container, then you're not calling a model, you're calling the container. And the distinction is now you can pass in additional parameters to a containerized workflow to say, don't just give me a simple output, consider these parameters of I don't want an output of a specific language identified in a contract plus its probability. I know you can give it to me, but just give me nix the probability. I just want the language. Or I want identified certain NLP language extracted from document of probability greater than 50% or greater than 75%, something arbitrary. You can pass those parameters in that API call to the Kubernetes container. And that Kubernetes containerized workflow would be looking for those parameters in the API endpoint call to say, all right, if then here's my function that defines how the model will be run. So it would be safer to opt for that Kubeflow containerized models in production as opposed to the MLflow just calling the same old model.
Yeah, but if you use MLflow and call like a Spark job in a Databricks environment, which does not use Kubernetes,
yeah,
scale, if not better, same. My understanding is same at least.
Sure. My understanding is it's similar. I just don't know enough about it. I'm sorry.
It's also just my personal understanding.
Can I ask a quick question before we wrap it up? When do you need to actually use Kubernetes and Kubeflow? Because this is obviously for container orchestration, and like how. I guess the direct question is how many containers. When you, I guess, what's the threshold of using that, as one of your two kids, like maybe it's 100 containers, 10 containers.
Do a Google search for kubeflow container limit.
Thank you.
That would be, that's a really good question. I don't know. I don't even know if there is even a processing cost involved with more containers. But again, this is where a lot of machine learning, especially in production, is all about the data engineering. It's the engineering these architectures that are far, far more valuable than the PhD data scientists monkeying around with data, trying to come up with clever models.
Yeah, yeah, cool. I mean, we're running out of time, and maybe we'll continue with some of the PyTorch basic data types next session. We do have enough time, as I think we have 4 sessions for this chapters as well. So we have enough time, and the extra time can probably be saved to talk more about PyTorch, because I think it will be a pity if we completely ignore PyTorch while we talk about TensorFlow, especially, you know, when it comes to these data types, and also how you customize models on the TensorFlow side versus PyTorch side. So, okay. On that note, I want to thank everyone.